how to solve it when we have laminar flow, turbulent flow, and how this will impact on my energy losses due to friction, which that could be using the Moody chart, or you could use the equations as well developed within the textbook. So this is chapter 8 from your textbook. You can access through WinTech library. Again, if you want more details, you can go through the textbook in more detail. This is just a brief. Um, So the contents will introduce the concept with define Reynolds number. Here, Reynolds number is just written in different way. We'll show you the difference. Critical Reynolds numbers, Darcy is equation, friction loss in laminar flow, and friction loss in turbulent flow. So those are the important flows we're focusing on. In between them, there's a transitional, and we'll talk about that later. So to introduce you, think about how the flow of water from a tap will come nicely, change depending on the velocity. If you open fully the tap, then you find the water will come like this. It's a bit white. You cannot see the particles are disturbed and pushing each other. However, if you open the valve, the tap really with the not of flow water going through it, you can see the water, you can see through it, and that's what shows like it's the flow, it's laminar, is not disturbed, and you can distinguish between the two flow regimes. And between them, that's where it's going to laminar to turbulent is the transitional area. If you haven't thought much about water flowing out of a tap recently, don't worry, others have, and a lot of different waters you can see it's became part of the design, how they can use lighting systems or how they can let the water come and leave the taps in different nice scenarios. What's the description of laminar, turbulent, and how can we define them? So laminar flow, this is how we describe the flow of water from the tap at a very low velocity. The flow appears to be smooth and steady. The stream has a fairly uniform diameter, and there is little or no evidence of mixing of the various parts of the stream. However, the turbulent flow, this is how we describe the flow when the tap is nearly fully open. The water has a rather high velocity and the element of fluid appear to be mixing chaotically within the stream. Reynolds was the first to demonstrate that laminar or turbulent flow can be predicted if the magnitude of the dimensionless number, now called the Reynolds number, is known, which is Re. Re is based on the properties for the fluid, such as density, dynamic viscosity, or kinematic viscosity, and the dimensions of the pipe, the fluid passing through, and the velocity, the average velocity. So the equation in this textbook, they refer to Reynolds number with a capital N and R, but other textbooks you find as R capital and E small letter. It's again the same concept, and the equation is related to VD rho divided by mu, velocity, diameter, density divided by dynamic viscosity, or VD divided by V, which is the kinematic viscosity because that represents the dynamic viscosity divided by the density. Reynolds number, as we mentioned, is dimensionless. It's used based on the SI system units. So you have the velocity in meters per second, diameter meters, and density is kgs per meter cubic, and then the dynamic viscosity, which is Pascal second or kgs per meter seconds. And then when you put these together, you find that all the dimension will be cancelled, and therefore this is a dimensionless number. The Reynolds number is dimensions as we stated, and this is the proof for how we cancel the units. You can go through them step by step. Note that all units can be cancelled, which is why it's called dimension. The Reynolds number is the ratio of inertia force on an element of fluid to the viscous force. So this is the definition of Reynolds number, is the ratio of the inertia force on an element of fluid to the viscous force. The inertia force is developed from Newton's second law of motion, which is the force equals the mass times the acceleration. Critical Reynolds number, that's when you decide if it's laminar or turbulent or transitional. So for practical applications in pipe flow, we find that if the Reynolds number for the flow is less than 2000, then we consider that flow regime is laminar. If the Reynolds number is greater than 4000, the flow can be assumed to be turbulent. In the range Reynolds number between 2000 and 4000, it's impossible to predict which type of flow exists. Therefore, we call this critical regime or transitional regime, depends on how you define it. And you get something similar. That I want to say sometimes for simplicity, we also assume 2000 or less or equal and bigger than 4000 or equal for turbulent. Some places you find it like that. Example, determine whether the flow is laminar or turbulent of glycerine at 25 degrees Celsius, flows in a pipe with a 150 millimeter inside diameter. The average velocity of flow is 3.6 meters. So you know that's what we say Reynolds is related to the properties, dimensions, and the velocity. So the equation will be Reynolds equals 150 must be divided by 1000, which is to compare that. We need to go to the textbook, the appendices, to find the material properties for glycerin at 25 degrees. What we need the density and dynamic viscosity, or just the kinematic viscosity. And you have the velocity. So from Appendix B, you can find the density for the fluid is 1258 and the dynamic viscosity 9.6 times 10 to the power minus 1 from same appendix for that fluid from the textbook. Reynolds number, the equation, velocity is given, the diameter we divide by 1000, you put all these number, velocity times diameter times density divided by dynamic viscosity, the number is 708. Based on the assumption this is less than 2000, the flow regime is laminar. And we insisting to work within the SI system units. Another example, determine whether the flow is laminar or turbulent if water at 70 degrees Celsius flows in a 1-inch type K copper tube with a flow rate of 285 liters per minute. Here is what's the difference in this question. Of course, you can work with high temperatures for water, 70 degrees, and flow in 1 inch. So even if we have inch type K copper, but we have the textbooks with appendices, so we can convert that to get the diameter in meters or millimeters, and then we convert that to meters. And also here is given to us the Q, which is 285 is liters per minute, which is the volume flow rate. So we need to divide that to convert it to meters cubic per second, and then the continuity equation, Q equals VA, V equals Q divided by A. So we find the area from the tables, appendices, and then that we convert it to meter cubic per second. We find the velocity and the material properties, and then we solve the question. So this is how it will be solved. For 1-inch type K copper tube, the diameter and the area are from Appendix H from the textbook. The velocity is equal Q over A. And we convert 285 liters per minute divided by 60,000 liters per minute to convert to meters cubic per second. And the area, as we got it from the textbook from Appendix H, you get the velocity 9.47. Material properties for the fluid water at 70 degrees from Appendix A, you get the kinematic viscosity. This is the other equation. We're not using dynamic viscosity. So you get the diameter multiplied by the velocity, 9.47 velocity, diameter, we just go from the appendix, divided by kinematic viscosity, which is from Appendix A. And therefore you find the Reynolds number, it's 5.82 times 10 to the power 5, which is bigger than 4000. Therefore the flow regime is assumed turbulent in this scenario. Another example, determine the range of average velocity of flow for which the flow would be in the critical region if E10 oil at 15 degrees Celsius is flowing in a 2-inch schedule 40 steel pipe. The oil has a specific gravity of 0.8 0.89. Again, if you see those dimensions, 2-inch schedule 40 steel pipe, don't worry, we have the appendix for them to work and convert them in SI units. So again, all the answers will be in SI units, but we need to understand how we work on the conversion. How can we also, if we have an oil at certain temperature, how can we work with a specific gravity for the oil? So the information given to us is not that much, but we want to know the range of average velocities of flow, or which the flow would be in critical region. So technically, we could assume the Reynolds number is about 2000 or 4000, because that the critical region, or any number between 2000 and 4000, and then we could find the cross-sectional area and diameter from the schedule of 40, and which is in this case we want the diameter because we want to find just the velocity, and the material properties for the oil. So the flow will be in the critical region. So as I mentioned, it's between 2000 and 4000. First, we use the Reynolds number and solve for velocity. So rearranging the equation, you have the velocity, you have Reynolds number times the dynamic viscosity divided by the diameter and density. Now to find the values for mu, this should be mu, not n, t, and density, we come here. The diameter from appendix F is about 52.5. There, remember, we need to divide this by 1000. And the dynamic viscosity is 1 times 10 to the power minus 1. That's for appendix T. And density for the oil, we multiply the specific gravity 0.89 times the water density 890, and then we put these values together and we get the velocity, and it's around 2.14 times 10 to the power minus 3 multiplied by Reynolds number. Now, for Reynolds number is 2000, you get the velocity 4.3. For Reynolds number is 4000, you get the velocity 8.56. So we have a range between 4.3 meters to 8.56 meters, representing for me the critical region. So this is kind of showing you, you can see it in the graph when we present the Moody chart, the range of the velocity in the transition. So it should be bigger than 4.3 meters per second and less than 8.56 meters per second, because as I say in many textbooks, they assume the 2000 isn't within the laminar and the 4000 is within the turbulent regime. Darcy's equation, it's based on using the general energy equation, which we just had it presented in the previous video. So general energy equation, to revise it, is the pressure head P1 over gamma plus elevation head Z1 plus the velocity head V1 squared over 2g plus HA, the head pressure added by the pump, minus HR, the head energy removed by the turbine, minus H losses, which is the friction and minor losses fittings, and equals to the other point we're trying to investigate. So this is the energy loss from the system due to friction, the length of the pipe. Therefore, that HL is very important because we need to determine the Reynolds number. And how can we determine that? There are two methods. One is for laminar and one is for turbulent. So one component of energy loss is due to friction from the flowing fluid, which is proportional to velocity head of the flow, the ratio of the length to the diameter of the flow stream in pipes and tubes. This is expressed mathematically using Darcy's equation. So HL equals the friction factor, which is dimensionless, could obtain by calculations or Moody chart. L, the length of the pipe, D, diameter, cross-sectional diameter of the pipe, V squared over 2G. All of that help us to find the energy loss due to friction, which is in meters or newtons meters per newtons. And length is in meters, D in diameters. Make sure the dimensions are equal, length and diameter. Velocity, meters squared per second, divided by acceleration. That's why they cancel. Those cancel the units, canceling the units. F is dimensionless, so HL will be only left as in meters. So because that would be meters square per second square, and this one meters per second square, so only left is the meters from here and canceling. And these are the definitions for them. So we use Darcy equation to calculate energy loss caused by friction in long straight sections of round pipe for both laminar and turbulent flow. The difference between the two is in the evaluation of the dimensions friction factor. So what they suggesting, because laminar flow is so regular and orderly, we can derive a relationship between the energy loss and the measurable parameters of the flow system. This relationship is known Hagen-Poiseuille law equation, which is HL equals 32 mu L V over gamma D square. This Hagen-Poiseuille equation is valid only for laminar flows when the Reynolds number is less or equal to 1000. Therefore, we could use the Darcy equation to calculate the friction loss in laminar. So we put the two equations equal. F over times L over D V square over 2G equals 32 mu L V over gamma D square. After canceling some of the parts, like you can see, the D will cancel with the square, V with the V square, and the numbers 32 will cancel as well, and mu and G you can find because the relationship between them, density is gamma over G, and Reynolds is VD density divided by mu. So all of that will end up to have a relationship called 64 over Reynolds. So that is F for laminar friction. For laminar is calculated based on this equation, 64 over Reynolds number. We still need to get this value F, and after we find it, we need to use it in this equation to find the losses through the, for example, suction of discharge line to determine the friction loss, energy loss. This equation, you can see the Moody chart very clearly, and I'm quite sure you've seen it when we did the scripting it in applied computation modeling in MATLAB. Let's see an example for it. Determine the energy loss if glycerine at 25 degrees Celsius flows 30 meters through a 150 millimeter diameter pipe with an average velocity of 4 meters per second. So here you have the material properties. You can obtain that from appendix. I'll tell you which one. Flows 30 meters through 100 millimeters, 150 millimeters diameter. So you have the length of the pipe, you have the diameter. Remember, we need to divide this by 1000. Must be the units all same. With an average velocity, and that's why I say we work with average velocity, 4 meters per second. Energy loss. So HL equal. First, you need to find the Reynolds number. Based on the Reynolds number, you determine the F. I assume this question will give us an F as a laminar, and then we'll see if it's turbulent, we'll see that. So to get the Reynolds number, I have the diameter, I have the velocity, I need the material properties, density and dynamic viscosity or kinematic viscosity. After finding Reynolds number, we determine if laminar, we use the F equals 64 over Reynolds, and then we use the HL loss F L over D V squared over 2G. Let's see that. First, we will determine the laminar or turbulence. That's what I mentioned. Reynolds number VD or rho over mu. And then in Appendix B, we find the material properties for the fluid at 25 degrees. We put everything together. We get it 786, which is laminar. And then that value is less than 2000. We confirm that. Now, to solve the energy loss due to friction, HL equals F L over D, which is Darcy equation, times V squared over 2G. L is given to us 30 meters. D is the 150 millimeters, but remember, we must divide it by 1000 to match the units. So it would be 0.15. F is the one we determine from this equation, 64 divided by Reynolds number. You get 0.081. And then V squared is given 4 meters per second divided by 2 times the gravity acceleration, 9.81. You get H loss as around 13.2 meters, or we call it Newtons meters divided by per newtons. But in many cases, we just say this is energy loss by hit or the distance meters. Now, friction losses in turbulent flow is slightly different. For turbulent flow of fluids in circular pipes, it's most convenient to use Darcy equation to calculate the energy loss due to friction. Turbulent flow is rather chaotic and is constantly varying, changeable. For these reasons, we must rely on experimental data to determine the value of F. Therefore, the F we found just by 64 divided by Reynolds doesn't work for turbulent flow. There are two methods. One is an equation using logarithms. Another one is using Moody chart. And the reason for that, because we need to take into account the wall roughness for the pipe, the inside surface of the pipe, as the height of the peaks of the surface irregularity. If you can see, the surface of the pipe is not really smooth. And because of the roughness is somewhat irregular, varying techniques are used to measure the overall roughness value, which you can see in the Moody chart. So you have D divided by E, or some textbooks E divided by D, but you must have the same units of dimensions, same, so they can be a ratio. So here, from the textbook, and I'll show you the textbook and other places where you use it, depends on how they assume things. Friction loss in turbulent flow. For commercially available pipe and tubing, the design value of the average wall roughness has been determined. These are only average values of new clean pipe. Some variation should be expected. I put a line. These are for clean pipes, not second-hand pipes, because by time the rust will build on the pipes and they will cause more energy loss in the system than before. After a pipe has been in service for a time, the roughness could change due to the formation of deposits on the wall or due to corrosion. So you have glass, the E roughness in meters is that value, and roughness in feet. So we are looking for the SI system in meters. So for plastic, for drawn tubing, for ductile iron, concrete wall made. Sometimes they use it in the old water and wastewater systems. Therefore, for this, as we say, we need experimental values. We use the Moody diagram or Moody chart. The Moody chart is one of the most widely used methods for evaluating the friction factor. It plots the friction factor F against the Reynolds number with a series of parametric curves related to the relative roughness, which is the ratio between the diameter and the roughness of the internal surface of the pipe. Sometimes in textbooks you see is E over D or D over E is the same. It's just the ratio will be slightly different, but it's the same process you follow. So in these textbooks, they use slightly from what you learned in last year in fluid mechanics or last semester. It depends when you took fluid mechanics. So this is the Moody chart. It's widely used. We used it in applied computation modeling, in scripting in MATLAB. We'll explain through with this. You get the material properties here. Again, it's slightly different from what I presented from the textbook. Materials, concrete, chorus in millimeters. These are the E roughness values. And here is showing you the friction factor, the final value we want to read. Here on the x-axis is Reynolds number. You have the equation RE, which, as I told you in other textbooks, is RE, not NR. Rho VD over mu, density, velocity, average diameter divided by dynamic viscosity. That scale is a bit funny, is because it's based on experimental data. So 10 to the power 3, which is 1,000, and this one 10,000. And then represent for you transitional region here. Around that region is highlighted in gray. This is the laminar flow. If it's you get laminar, you straightforward, you find the F by 64 divided by Reynolds, so you don't need to use this chart. However, if you are turbulent, your flow is more bigger than, equal or bigger than 4,000, then you need to find Reynolds number, intersect with the ratio. What ratio is relative pipe roughness, which is E over D. In the textbook is D over E, so these numbers will be bigger. It's just like the inverse of these numbers. And then make sure that D is in millimeters because E is in millimeters or vice versa. That's ratio must be the dimension cancel. So you come here, you intersect with the blue lines, and then you read from the other side on the y-axis friction factor. Now, in MATLAB last time, when you did MATLAB with me in scripting and applied computation modeling, we use this equation, F friction factor. This equation is based on this experimental data. I strongly recommend you use this equation. You just set it up in Excel file and to perform for your design, because you don't want to use this, what I call it, the chart every time since you're doing a design problem. You can use materials embedded in your structure of Excel file, and these materials, every time you have a selected a type of pipe, you just bring the E and make sure the units are matching the diameter, and then when they change the diameter, or you calculate the Reynolds number, and then you get the F automatically without really going through the process to avoid this application. You can do everything, that's why I'm saying, in the design of your pump station using the Excel file, which is what we'll be doing in. But that's what we tested. We experimented with even MATLAB, and it works and no problems. So the Moody chart or Moody diagram, several important observations can be made from these curves. For a given Reynolds number of flow, as relative roughness is increased, the friction factor F decreases. For a given relative roughness, the friction factor F decreases with increased Reynolds number until the zone of complete turbulence is reached. Within the zone of complete turbulence, the Reynolds number has no effect on the friction factor. As the relative roughness increases, the value of Reynolds number at which the zone of complete turbulence begin also increase. This is what it's going through it. So simplify sketch the Moody diagram in which the various zones you're showing here. The laminar is about 2000, and then the critical zone or transition zone 4000, and after that start creating those relationship between them. As I mentioned, the textbook used D over E, so the diameter divided by roughness to give you the relative roughness. That's why you see the numbers is 20, 50, 500. However, in the Moody chart, you'll see is 0.05. It's just the inverse of these numbers. So don't be shocked about that. It's the same. As long as the units are equal in whatever method you use, it should be the same. But my recommendation for you, use this equation for turbulent, use this equation for laminar to determine the F friction factor value to calculate Darcy equation. Example, just we go through it very easily, and I recommend you try it as well to try to solve it using the Excel file. Determine the friction factor F if water at 70 degrees Celsius is flowing at 9.14 meters per second in uncoated ductile iron pipe having inside diameter of 25 millimeters. So it wants you to find the F friction factor. F, it's required to find it by using the Reynolds number. From Reynolds number, you determine if it's laminar or turbulent. If it's laminar, it's 64 divided by Reynolds is the F for laminar. If it's turbulent, you can use the equation or you can use the Moody chart. It's up to you. But when you have a big problem design, the equation will be very easy and faster. So you especially when you're doing iteration, because this what we're building at the end is for your design question. So the basic what you done before when you study fluid mechanics, you determine Reynolds number, you got all the information from the appendix. Appendix A will provide you with the material properties of water at 70 degrees Celsius. You get the velocity is as given, the diameter is given, the kinematic viscosity from the appendix, and then you find the flow is turbulent, 5.6 times 10 to the power 5. That flow, you have the material is uncoated ductile iron pipe. You go to the relative roughness 2.4 times 10 to the power minus 4 meters, and then you find the ratio is D over E. As I say, that's why the textbook in our what you learned in the past is E over D, and make sure the units are the same, and then you get that 1 divided by 104, and then you get the small number. It's the same concept. But if you use the equation, that's what I've been trying to say, it's D over E as well. So it's something you work with it and you just get that ratio right. And then based on it, you go to Reno Moody chart, you locate this value 5.6 and project vertically onto the curve of D over E using the Moody chart from the textbook. And this can be found to find the F in a project horizontally. I will show you that in this. So I will take these values. So we got the 5.6. So you allocate the 5.6, you find the D over E. In this case, you will be the E over D. You just inverse 100 by 5, and then you intersect whatever is coming this with the blue lines, the dark blue lines, and you read the value 0.85. Based on the answer is given, the value is 0.038, 0.038. So it will be here around this point. So it's intersecting with this line with something around this point. So just showing you. However, if you use the equation, it should be very quick and doesn't really take that time because you set it up one time in Excel file and then you just select the values and you go through it. I will leave this question for you so you can do it, and I'll give you some examples, some homeworks to do during study, but we'll do this one as well. In a chemical processing plant, benzene at 50 degrees, specific gravity 0.86 must be delivered to point B with a pressure of 550 kilopascal. A pump is located at point A, 21 meters below point B, and the 2 points are connected by 250 meters plastic pipe. So we know the material of the pipe having an inside diameter, the inside is 50 millimeters. If the volume flow rate is 110 liters per minute, calculate the required pressure at the outlet of the pump. So this question is very interesting and is showing you a lot of information given. First, pressure at point B is 550 kilopascal. Plastic pipe, 240 meters, 50 millimeters diameter. The direction of the flow going that way. And the Z elevation, if we take this as a reference point 0, is going to point B is 21 meters for the pump. We're working after the pump. And they want us to calculate the required pressure. So the pressure at point A, the outlet of the pump to deliver that. So to start with these type of questions, we always start with the general energy equation. Because in the general energy equation, you write it P1, Z1, PA, gamma, ZA, VA squared over 2G minus HL. Why minus HL? Because we are taking a point after the pump. So after the pump, we have the following points from A to B. So it's only H losses in the system. There is no pump, no turbine, nothing else than losses due to friction, and possibly if we take into account the fittings. So you rearrange the equation. VA, it's assumed as constant, is not 0. They will cancel each self because it's a constant diameter from here to there. So using the continuity equation, Q equals VA equals VB, and because the diameter is constant, therefore the VA and VB are constant. They have the same velocity because you will have the same volume flow rate, which is 110 liters per minute. So that term is not 0. It should be cancelled. That's one of the things to correct. This is from the textbook. And then you have pressure at point B is given 550 kilopascal divided by gamma, the gauge pressure. Rearranging this equation, gamma ZB minus ZA. So if ZA is the reference point 0, ZB is at 21, so that term is 21. As you can see it here, positive, plus HL, because HL will move to that side to stay the PA here, and that will be just multiplying by gamma. Gamma will be cancelled from that side. So the evaluation of Reynolds number is the first step. We need to know if this is a laminar or turbulent flow. So we have Q. we have velocity. We could determine the density based on water, and we could find the dynamic viscosity. So important information, please. Every time in here I mention the appendices, that's where you can find the properties. So please pay attention to these appendixes from the textbooks because in your design question you need them. So for a 50 millimeter pipe, diameter is 0.005 meters, area it's this value. You have the Q converted from liters per minute. We divide by 60,000 to make it meters cubic per second. Velocity is Q divided by A. You have the area, we just convert the Q, you get the velocity 0.932 meters per second. Density, because we're giving the specific gravity multiplied by density of water at room temperature 1000, you get the density of that fluid. The fluid is giving, and this is benzene, so you can get it as about 860 kgs per meter cubic. From Appendix D, you can get the dynamic viscosity. Reynolds number would be the velocity multiplied by the diameter, multiplied by density, divided by dynamic. You get a turbulent value because it's bigger than 4000, is 9.54 times 10 to the power 4. So it's technically is turbulent flow. And therefore, we need to use Darcy equation for this application. HL equals F times L over D times V squared over 2G. So from table A2, roughness is 3 times 10 to the power minus 7. This is 10 to the power minus 7 meters. Then we could find D over E, 0.05 meters, and this value in meters. You get it 166,700. And then based on that, we intersect the D over E with the Reynolds number, and then you get a value for F 0.018, and that value you add it into Darcy equation, F L over D, V squared over 2G, 0.018, 240 divided by 0.05. 240 is the length of the pipe. This is the diameter. Velocity we find, as I say, is a constant. AV, and VB are the same. And then you get the H losses due to friction. And then you bring that H losses into the system. You have the equation we just set up here. So PB is 550 kilopascal. This is specific gravity times the specific weight for the water. 21 is the elevation. This 3.83 meters is represent for me the H losses due to friction. You add them, so the pressure will be 759 kilopascal. Now, one thing I will mention about this question, which is made as an assumption, it's we only calculated the friction loss due to the length of the pipe, but in reality, we need to take this into account as well. If there are any elbows in the design, those we call them minor losses, but because we haven't introduced how to calculate minor losses yet, so that we assume them, we neglect them in this as this stage. But in reality, in your design questions, you need to take them these two elbows into account, and take these elbows into account to calculate the H losses for them. It's K, the resistance coefficients, multiply by V squared over 2G. And if there are two of them with the same angle, same value of K, so it'll be 2 times K V squared over 2G. Which V we use? It's VA, because that's the velocity passing through them. And then you get the H losses due to minor fittings plus the H losses due to friction. So you will add that value 3.83 plus that minor losses, and then you will add a bit of it. Now, because that number will be smaller, that's why it was mentioned, yes, like in the other video, they can neglect it and assume it just doesn't exist. So this is a quick revisions from your textbook. My advice for you, this, by the way, exists in your textbook, so it's nothing, it's new in all your books available. My advice is to be familiar with the appendices. Just go through the end of the textbook, go and find Appendix F, Appendix D, and the other appendices where you can find the properties or the dimensions for the pipes and anything you want. Appendix H, for example, for the type K copper tube, and they have different appendices. And hopefully we'll see you again, and we'll try to solve some problem with fault design. Also practice on how can you set up this in Excel file and how you set up this table in Excel file, because it will save your time when you try to select different materials, or you can have one value for it. Thank you very much. We'll see you very soon with another video.